Well, our time today is finite, so if you haven't gotten this far, then perhaps you are not prepared to do this. Um, I do want to remind you to tell you how to get the 6.3 and the 5.5. Okay, I'm going to be honest. You should know how to do it. Dropping a ball and figuring out how fast it goes. Right, we're talking about September, right? You could do a motion equation and figure it out. Or just our very last unit. If you drop the ball from here, it's got gravitational potential energy. What kind of energy will it have just before it reaches the ground? Thank you. This is going to be rough, guys. If nothing takes energy away from when it was dropped to when it reaches the ground, then these two have to be equal. If you don't like that, then delta y, v, v naught, v, a, t, you could do that too. You have options, folks. It's going to be rough. It's going to be rough. So I'm going to go with mgh equals 1/2 mv squared. And use that to figure out how fast the ball is going when it reaches the ground. So cancel out the m's and I'll get v is equal to the square root of 2gh. And that gives me 6.3 meters per second over here. It's the same thing over there. It just starts with kinetic energy here and goes upwards. Does the ball have the same amount of energy after it bounces? No. How do you know it doesn't have the same amount of energy after it bounces?
Because it slowly stops bouncing.
True, but what's an indicator that the ball has less energy after it was dropped?
It doesn't bounce as high.
It doesn't bounce as high. Yep. If you can answer that question just like you did, you'll probably be able to answer most of the fill in the questions on your coming up test about energy and momentum. Because they're going to ask you questions about how you know things. That's a reasonable question to ask. Now, we have the two velocities, so the rest of this does default to what we did yesterday. So I'm going to zoom in a little bit. Impulse is equal to change in momentum. That's on the board behind me. And momentum is defined as mv. So this is mv final minus mv initial. We just spent a few moments finding the final and the initial. This is the final. This is the initial. Mass of the ball, 0.5. So 0.5 times 5.5. We forgot to do something now. Something that we tend to forget, but I tried to put infinitors. We have to choose a direction we call positive. That's what these little bars are about. So we should do that. Do you want downwards to be positive or downwards to be negative? Down positive? Okay. That means when the ball comes back up, it's got a negative velocity. Minus 0.5 times 6.3. That's it. This gives us our 6 kilograms meters per second. This is the impulse. Because it's negative, that means it's upward. The ground pushed up on the ball. I'm not really surprised. It was a normal force. How much force did the ground apply to the ball? That's the other side of impulse. Right, it's on the board there. The other side of this is net force times time equals impulse. We were told the time is 0.003 seconds. I think you guys can do the rest of this math to figure out that it's about 200 newtons of force. Now, look, I'm little frustrated, but we're at the end of the year, guys. I have to expect you guys to remember stuff we did in prior units. If I can't, you're the ones who are going to pay that penalty, not me. This problem had a little bit of impulse in it and a little bit of conservation of energy in it. It is a fair test of your abilities. I'd say this is actually a pretty straightforward question. And look, there's more than one way to do these problems. Here, follow me for just a minute, please. Net force times time equals mv final minus mv initial. Right? We just wrote that on the board. Divide both sides by t. All right? That makes this side net force. And this side, I'm going to collect the m. Right? There's m's in both top terms. I'm going to collect the m out of it. And that makes this v final minus v initial over t. And you might not recognize what that is, but you had a motion equation at the beginning of the year, right? Does that look familiar? Subtract vi from both sides. Divide both sides by t. It's just Newton's second law. We've been doing this since the very beginning of the year. There is nothing new. And you guys who couldn't figure out how fast it was going, mgh equals 1/2 mv squared. This was v final, right? Right before it reaches the ground. What was the initial velocity of the ball when it was dropped? 0. Now, the reason I'm writing this down is I want you to remember when this ball was dropped, the initial velocity was 0. But let's just put the term in place. There would have been kinetic energy there if it wasn't 0, correct? That seem reasonable? Subtract this term from both sides, and I get mgh equals 1/2 mv final squared minus 1/2 mv initial squared. Do you notice that every term has an m in it? So we could get rid of all the m's. That okay? So that's now gh equals 1/2 v final squared minus v initial squared. We'll multiply both sides by 2, okay? That'll get rid of the 1/2s. And I know you don't know where this is going, most of you, but what is g? The acceleration due to gravity, correct? For this problem, it was the acceleration. What was h? It was how far the ball moved, right? The displacement of the ball. It's all the same stuff. So I have these two cars here, and I want to figure out where their center of mass is. Let's say one of the cars has a mass of 0.75. The other one has a mass of 0.5. And let's say they are separated by a distance of 1.5 meters. So they're just basically on a track like this. One of the cars is a little heavier than the other car. So the heavier cars over there, they're about 1.5 meters apart. I want to find out where the center of mass of the system is. We've talked about this problem before. The center of mass is a place. It's a location. And to find the center of mass of the system, you're supposed to do two summations, right? There's one summation divided by another summation. The top summation is the mass of each object times each object's location. And you start with the first object and add all the objects up. How many things are we going to be adding up? How many objects are there? That's the easy question. So we'll be adding 2 things up on the top. On the bottom, we just add up the mass of each object. Starting with the first object, ending with the last object. Again, how many objects are there? 2. Now, to do this, we have to have an agreed upon place that is our reference point. We could make it the end of the track, or we can make it one of the cars. Where would you like to make that? one of the cars. So that makes one of the cars the location 0. Easy enough. That means the other car's location is what? It is not 0. True. What's the number? 1.5. It is 1.5 meters away from the first car. So let's do it. You could do this. You don't need my help here, right? You could plug these numbers in and find out where the center of mass of the system is. I'm sure you have notes from way back when we did this that tell you how to do it. But you probably couldn't find them right now if you wanted to. Some of you could, not all of you. But I'm just going to follow the instructions that are on your equation sheet that tell us how to do it. It says take the mass of the first car, 0.5, then multiply by where that first car is, 0. Then go to the next car. Take the mass of the next car, 0.75. Multiply by where that car is relative to the first car, 1.5. That's 2 objects. I've added them together. Moving on to the bottom. The bottom, take the mass of the first car. Add the mass of the second car. There it is. That's it. That's all you have to do. Now, I know you're writing everything down that I'm writing on the board, but that's useless to you, right? Because you're just going to have a bunch of numbers when you're done, and tomorrow I'm going to ask you to do something, and you're just going to look at the blank piece of paper in front of you, just like you did today, and get nowhere. Do more. Write some things down to help you. Spend the 5-10 minutes getting those notes to be nice and prepared. I have an answer. Do you have an answer? I got 0.9 meters. It's a location, though. It's telling me that from the first car, it is 0.9 meters away. 0.75 would be the midpoint between them. 0.9 means it's closer to the heavier car than the light car. Does that make sense? Okay, good. Now that's old. I just want to do that to remind you of how to do this. Because today we have something new I want to add. So I want to do something different. What if this car were moving at 2 meters per second? Would the center of mass stay in place? Or would the center of mass also be moving? Center of mass would be moving because the 2 cars are getting closer together, right? So I need you to be able to calculate the velocity of the center of mass of a system of objects where they could be moving. And I'm not going to prove this to you, but it's the exact same thing as calculating the center of mass. It's just that you switch out position for velocity and use that to calculate the velocity of the center of mass. Now, I do want to point something out very, very, very critically, because this is a little different than what we just did. And if you are really paying attention and look at the board behind me, you'll realize that the top of this fraction is the sum of the momentum of the system. Right? MV. So the top is the momentum of the system divided by the mass of the system. And that's important because we're going to be using the sum of the momentum of the system a lot today. So knowing that the velocity of the center of mass is related to the momentum of the system is important. And this is going to be important. We're still dividing by the mass of the system. This is how you calculate the velocity of the center of mass. Please take a second and verify the velocity of the center of mass. I know what the answer is. I'm going to write it right up here where you can't see, but I can see it. It is right there, hidden away. Try it. I'm going to pick one of you. I'm rolling the dice today because I'm frustrated. I'm going to do the stuff at the top first, right? Because it's a fraction. What's the mass of the first object? 0.5 kilograms. What's the velocity of the first object? 2. What's the mass of the second object? Excellent. What's the velocity of the second object?
Zero.
0. Did you put its location?
I know I put 0 for the other one too.
Oh, no, it's not moving. So then we take and just add the masses together. And we found your mistake, so we're good to go, right? Excellent. That gives us our 0.8 meters per second. Now, okay, what I need to talk about now, big stuff, important things. The most important thing I'm going to talk about today, ready? Impulse says that net force times time equals the change in momentum. This applies to an object and it applies to a system. What we have on the table here is a system, right? It's multiple objects. That's all a system is, multiple objects. So if we talk about the system, okay, now listen closely. If the net force on the system is 0, then the change in momentum of the system has to equal 0. So if there's no external force on the system, the momentum of the system is constant. Okay? I'll say it all over again. If we have it, like right now, what I have on the table in front of me is 2 cars. They constitute a system. They are at rest, and there's very little friction there, and I've balanced the track so it's not leaning one way or the other. That means the net force on the track is 0. That means that there can be no change to the momentum of the system. So the system's momentum stays the same. Now right now that's really boring because my track, neither car is moving. So as long as there's no force on the system, they just stay not moving. But this is also a statement of Newton's first law. Remember in Newton's first law, it says that if there's no external force, then the system remains at its velocity forever. Right. Now, in this case, the velocity of the system is 0, but what this also would say is if the car had a velocity of 2 meters per second, that would mean the momentum of the system is 1 kilogram meter per second, right? Because 0.5 times 2 is 1. So that has to be the momentum of the system forever until a force acts on the system. Now, if we follow this to its logical conclusion, do you realize the first car is going to eventually hit the second car? That does not change the momentum of the system. And I'm going to prove why, because it's important for me to prove why. But think for just a minute that in a second there's going to be a collision. What that means is that the first car is going to hit the second car. Hard, mind you. 2 meters per second is not slow. So consider advancing this to that point. So car 2, car 1. Right, they have an accident. Right, one car hits the other. I still want to use the rules of this unit. Car 1 pushes on car 2. Right? Newton's third law says car 2 pushes on car 1. Those forces have to be equal. Correct? Because the force on car 1 has to be equal and opposite to the force on car 2. Right? This is what we learn. Can car 1 touch car 2 for a different amount of time than car 2 can touch car 1? Like if car 1 stops touching car 2, can car 2 still be touching car 1? No. You've played this stupid little game when you were a kid. I'm not touching you. I'm not touching you. Do you know what I'm talking about? Technically, it's annoying as heck, but if you are, like right now, if you touch your finger to the table, can you take your finger off the table, but the table's still touching you? No. What's that?
If it's touching your leg.
Wow, we're talking about your finger. The reason I'm saying, and this part's, I'm trying to be very technical here, but if we multiply both sides of this by t, how long they're in contact, it would tell you that the impulse on car 1 also has to be equal and opposite to the impulse on car 2. This is also Newton's third law. Newton's third law applies to impulse and force. That's going to get more complicated in a second, so pay close. This is the change in momentum for car 1. And this has to equal the opposite change in momentum for car 2. So stay with me. Delta means final minus initial. So for a few seconds, we're going to focus just on this. P final for car 1 minus P initial for car 1. That's the left side. Equals negative times P final car 2 minus P initial car 2. Everybody see all this okay? I'm going to distribute the negative sign. Okay? I'm going to take the stuff that's negative and move it to the other side of the equation so that everything is positive. Is that okay? So I'm going to take this term and move it over there, and this term and move it over here. This puts all the finals on one side and all the initials on one side. Is that okay with you guys? So P final for car 1 plus P final for car 2 has to equal P initial car 1 plus P initial car 2. Now, I know implication is hard for you guys, so let me help spell out the implication. This says if you add up all the momentum of the system, this is the system's momentum before the collision, it has to equal the system's momentum after the collision. That's what we just said. The momentum is a constant. So if there's a collision, any collision in nature, the momentum of the system before the collision has to equal the momentum of the system after the collision. This is true for every collision in nature. For every collision, the momentum before equals the momentum after. Again, true for every collision in all of nature, regardless of what happens in the collision. Now, this is actually true in 3 dimensions. We're going to focus in 1 dimension, but it's true in all 3 dimensions. Now, to kind of play around with that, let's consider what a problem might look like, okay? We're going to do 3 different kinds of problems here. So to do this, I am going to kind of start fresh. Come on, be my friend. All right, let's start with this problem right here, and let's do a collision in which after the collision, the 0.75 kilogram car is moving this way at 1.5 meters per second. Okay? Now, I didn't say how fast this car's going, the second car. That's what we want to figure out. How fast is this car going? And I don't know what direction it's going either, to be honest with you. It could be going to the left or to the right. That's what our answer is going to tell us. But these are momentum problems, so before we get started, we decide what direction we want to make positive. And I'm deciding for you, I'm going to make this direction the positive direction. But this represents the before case. This represents the after case. But the momentums have to be equal. So we're going to add up the momentum of the system before the collision. Let's start with that first. So the first car has a mass of 0.5 and a velocity of 2. The momentum of the second car has a mass of 0.75 and a velocity of 0. This is the momentum of the system. Whatever this is the momentum of the system before and after the collision. We already know this is 1. This has to be equal to the 0.5 kilogram car times an unknown velocity. We don't know how fast it's going. That's what we're looking for. But the other car we know has a mass of 0.75 and a velocity of 1.5 meters per second. That's known. And we're going to use it to figure out what the other car's velocity is. Now the left side, we've done this a couple times. It's 1 kilogram meter per second. This is going to be 0.5 times v plus, well, I have to do 1.5 times 0.75. 1.125. Going to subtract that from both sides and get 0.125 equals 0.5 v. And then all I got to do is divide, and I get that my velocity is negative 0.25 meters per second. So which way does that car go after the collision? To the right or to the left? To the left, because we said to the right is positive. And isn't that what we just saw? This is called an inelastic collision. Most collisions in nature are inelastic, which means they do not conserve kinetic energy. They only conserve momentum. All collisions conserve momentum, all of them. But there are 3 classifications of collisions. The most general classification are inelastic collisions. They conserve momentum, but they don't conserve kinetic energy. Said it 3 times. Do I need to say it 4th? Inelastic collisions. They conserve momentum, but do not conserve kinetic energy. I want to take a look at another kind of collision. Are you ready? I don't really care if you're ready. We have to do these. There's 3 different kinds. And we're not going to be able to see all 3 kinds because one of them is exceptionally rare. So we won't see it. But I want to do one where the cars stick together after the collision. Now, again, we can do this. In our perfectly inelastic collision, the objects will both have the same velocity after the collision. In a perfectly inelastic collision, the objects will have to have the same velocity because they stick together. But again, in these collisions, momentum is conserved. And because momentum is conserved, the momentum before equals the momentum after. So afterwards, I really just have one car, don't I? That has a combined mass of 0.5 plus 0.75 because they're joined together and they will have the same velocity. How fast are they going? And you've already done this problem. You did this earlier today. You're going to find out in a minute what the answer is, and you'll see something important, I hope. Go ahead. Everything's going to work out similar. This side is still 1, right? Nothing about this has changed. This side is going to be 1.25 v. And what do you get? 0.8. That's right. You got the velocity of the center of mass, right? They're joined together, so of course they're moving at the velocity of the center of mass. There's only one object now, right? So of course it has the velocity at the center of mass that the system would have. That's also the reason why we call it a perfectly inelastic collision. because at the end of this collision, it will have the velocity of the center of mass. Now, there's one more kind of collision. We're not going to do the problem in here because it's kind of mathematically complicated. But you have to understand it's something that could be asked of you. It's called an elastic collision. In an elastic collision, it's special because in an elastic collision, both momentum and kinetic energy are conserved. So I'll say that again. In an elastic collision, both momentum and kinetic energy are conserved. So what that means is you have to add up all of the kinetic energy before the collision.
Good afternoon, Sickles. This is just a reminder. It will be too late to vote. So get down here and cast your ballot if you haven't already. Thank you.
So although this is true that both cars will have some velocity, because the kinetic energy is also conserved, you can say that the kinetic energy before, which is almost all the same kind of stuff, has to equal the kinetic energy after. Now that, as you can probably see, becomes a pretty complicated and maybe a harrowing kind of problem. Do you see what I mean? Because there's all sorts of equations and squares and stuff. This might be a little outside our scope. You need to be able to describe what a elastic collision is. You have to be able to say the kinetic energy before equals the kinetic energy after. That's something you need to be able to say.